What's a derivative? And I don't mean the formula. I mean the actual thing. If I stopped you on the street and asked, you'd probably say the slope of the tangent line. Or maybe the rate of change. And sure, those will get you full marks on a test, but they're telling you what a derivative does, not what it is. And the difference turns out to matter a lot, so let's build the real picture, from the ground up. Here's a curve, just some wiggly thing, let's say sine of x plus a little upward drift so it doesn't repeat. It bends. It does curvy things. Pick a point on it. Any point. We'll mark it with a dot. Now let's zoom in. Right on that dot. Closer. Closer still. Watch what happens. The curve, which was clearly bent a second ago, it's flattening out. Keep going. And at some point the curve just isn't curved anymore. It looks like a straight line, a perfectly ordinary line. And this is the thing I want you to sit with, because it's kind of amazing. That's not the animation cheating. Every smooth curve does this. Zoom in far enough on any nice smooth function, and locally, right up close, it looks like a line. There's a name for it. Local linearity. And it's the whole foundation of calculus, even though almost nobody says it that way. So here's the reframe. At every point on a smooth curve, there's one special straight line. The line the curve is pretending to be, right there, up close. The derivative is just the slope of that line. That's it. That's the number. The thing that tells you which line, out of all the lines you could draw through that point, is the right one. Now, the textbook calls that the tangent line, and that word kind of undersells it. Tangent sounds like geometry homework, a line that touches the curve and doesn't cross. True, but boring. The reason we actually care is this. Look in a tiny window around our point. The line and the curve sit right on top of each other. They're basically the same. So if you wanted to know where the curve goes, just a hair to the right of the dot, you don't need the curve at all. Use the line. And you'll be right. Not roughly right. Right in a really precise way. The gap between the line and the true curve shrinks faster than the step you take. Step half as far from the point, and the error drops to a quarter. That's what makes this whole thing worth a damn. You get to throw away the complicated curve and use a simple line instead. And the swap is almost free. Okay, so how do we actually find this line's slope? Here's the honest trouble, we don't have the line yet. The line's what we're after. All we've got is the curve. So we fake it. Pick our point. Now pick a second point on the curve, a little way over. Call that gap H. Draw a straight line through the two of them. That's not the line we want. It cuts across the curve instead of hugging it. But its slope we can compute. Rise over run. The height at x plus h minus the height at x all over h. Simple. And now the move that makes calculus calculus. Slide that second point in toward the first. Shrink h. Watch the line swing around as the point slides, closer. And in the limit, when h goes to 0, that cutting line settles down onto the line we wanted all along. The fake becomes real. So when you write f prime of x equals the limit, as h goes to 0, of f of x plus h minus f of x over h, that's not a magic spell. It's a recipe. Fake the line with 2 points, then squeeze them together till the fake turns into the truth. Read it that way, and you can't unsee it. Let's settle one more thing while we're here, because it bugged me for years. Your teacher swore up and down that dy over dx is not a fraction. It's one symbol. Don't you dare cancel it. And then a week later, doing the chain rule, they cancel it. So which is it? Here's the honest answer. Once you've got the local line in your head, dy over dx really is a fraction. Watch. We're on the local line now, the curve's pretending to be straight. Take a tiny step to the right, call it dx. The line rises by some amount, call that dy. And on a straight line, the rise over the run is just the slope, dy over dx. Two little numbers, one divided by the other, a real honest fraction. The warning you got was protecting you from using it where the curve still bends. But right here, on the local line, where derivatives actually live, It's a fraction. And that's the payoff. The chain rule, basically for free. Say x feeds into one function and gives you u, and u feeds into another and gives you y. Nudge x by a tiny dx. Because the first function's locally aligned, u moves by its slope times dx. That's du. Now u moved by du, and the second function's locally aligned too, so y moves by its slope times du. That's dy. String it together, divide through by dx, and the chain rule just falls out. You didn't memorize a rule. You watched two lines pass a nudge down a chain, each one multiplying by its slope. So, next time somebody asks what a derivative is, you've got a better answer than slope of the tangent line. It's the line your curve is pretending to be. The slope, the rate of change, the weird limit, that fraction notation, the chain rule, all of it falls out of that one picture. If you enjoyed this video, please subscribe and watch my video about computing pi.